In today's video, we're going to look at the impact that temperature and pressure has on equilibrium, and when these things change, what happens to equilibrium. So in the previous video, we discussed what equilibrium was and what happened when the concentration was changed. So if you haven't watched that, I would recommend watching that before moving on to this video for you to be able to access this video fully. So we're going to start with temperature. So I've got the same equation from last time. We've got nitrogen and hydrogen making ammonia. All I've added on here is exothermic and endothermic because that's really clear, key point when we're looking at temperature and what happens to temperature when we either increase it or decrease it. Because remember, equilibrium, Le Chatelier's principle is that equilibrium will shift to ensure that that equilibrium is reached again as quickly as possible. So when we're looking at temperature, first one we're going to look at is an increase in temperature. So if an increase in temperature happens, and I'm going to do this in a different coloured pen so you can see, it favours the endothermic reaction. So it favours endothermic reaction. Now you might wonder, why does it favour the endothermic reaction? And that is because endothermic reactions, they take in heat. So if the heat is increased in that container or wherever it is that the equilibrium is happening in that closed system, if that temperature is changed in that system and it's increased, the equilibrium wants to get it back to that same level it was earlier so that the rate of reaction of the forwards and the backwards can be at the same rate. And therefore, if it favours the endothermic reaction, which is the type of reaction that takes in the heat, then it's going to be able to reduce that heat in the container, in that system, so that it gets back to the equilibrium level. So you could add maybe a little bit of detail to your notes if you're making notes, that actually it favours the endothermic reaction because it takes in the heat and it reduces that temperature back down. For decrease in temperature, we're a little bit different. It's going to be the opposite. It's going to favour the exothermic reaction. So it's going to favour the exothermic reaction because exothermic gives off heat, so that heat can be used to get back to the equilibrium. It can increase the temperature of the system. So this one favours the exothermic reaction, and that is because exothermic reactions give off heat. So as we're giving off more and more heat, then we can get back to the original temperature, and then equilibrium can be happening, and both reactions can happen at the same rate. So that's all we need to know for temperature. And for pressure, it's a little bit different. So I've changed the equation because it has to be an equation with gas particles in it, because you can change pressure in gases. So it has to be when we've got gases in here. So if we were to increase the pressure of this system, what's going to happen? Now it's going to shift to the side which has less moles of gas. So if you have a look at this, there's an imaginary one in front of there and an imaginary one in front of there, and you should know that. And there's a 2 in front of here. So this side, there is 3 moles of gas. Whereas on the red hand side, on the right hand side, there's just 1 mole of gas. And that's really key when we look at pressure, because an increase in pressure, what happens is it shifts towards the side with the least moles. So an increase in pressure is going to shift to the forwards reaction because it wants to have the most moles. So it's going to shift to the side with the fewest moles of gas. And you can simply see that by looking at the numbers in front of each molecule. So if that's the case when we increase the pressure, and we're going to the side with the fewest moles to try and get that back to equilibrium, so the rates of the forwards and backwards reaction are equal. If we're looking at decrease in pressure, it is, yes, it's going to be the opposite way around. It's going to favour the side with the most moles. So it's going to shift to the side with the most moles of gas. And that is really key. The pressure can only change when we've got gas. And that's for rate of reaction and equilibrium. We can only look at those equations that are about gas and talk about how the change in pressure could change equilibrium or change the rate of reaction. So just to go over this, an increase in pressure of the system, you would shift to the side with the fewest moles, whereas a decrease in pressure, you would shift to the side with the most moles of gas, making sure you're talking about gas, not liquids or solids.